Ever looked at like a crackling fire or a speeding car and wondered, what exactly is energy?
Hmm.
I mean, most of us, we kind of get it, right?
Right.
Like it's the stuff that makes things move, that powers our world.
Yeah.
But what if I told you we're diving into this mystery Feynman style?
Oh,
Yeah, today we're cracking open excerpts from Richard Feynman's legendary physics lectures.
okay.
And trust me, this isn't your high school physics class.
No.
This is about grasping the core of energy, what it is, how it morphs, and why it's more mind-blowing than you might think.
Feynman had this incredible gift for taking the utterly complex and making it feel like this elegant puzzle you just have to solve.
Totally.
Right.
He won a Nobel Prize, but he could also explain these wild ideas in a way that just clicked.
Yeah.
And get this, he used a story about Dennis the Menace to explain energy.
Oh.
Ready for this?
Classic Feynman. Finding physics in the everyday. Go on.
Okay, so picture this. Dennis is home alone, stuck in his room with 28 indestructible blocks.
Okay.
You know the kind, can't break them, can't lose them.
Right.
His mom notices something strange. No matter what kind of chaos Dennis unleashes, there are always 28 blocks at the end of the day.
Right. It's like a fundamental law of Dennis's world. The number of blocks never changes.
But then it gets interesting.
Okay.
Sometimes a block goes MIA, only to turn up under a cushion.
Yeah.
Or the window's open, a couple of blocks took a surprise trip outside.
Right.
Suddenly it's not so simple anymore.
Exactly. Dennis's mom needs a more complex way to account for these hidden blocks, and that's where the analogy starts to reveal something about our universe.
Okay, so how does Dennis's mischievous afternoon connect to, you know, actual physics?
Those blocks, they represent energy.
Oh,
Just like you can't create or destroy those indestructible blocks, energy can't be created or destroyed either. It simply changes forms or moves from one place to another.
So it's always got to be somewhere doing something.
Exactly, and this is where things get even cooler.
Okay.
Just like those blocks hidden under the rug, energy has different forms. Gravitational, kinetic, heat, light, even mass itself is a form of energy. That's Einstein's famous EMC.
Whoa, hold on. So that cup of coffee over there, mass, energy. Are you saying my coffee is basically a tiny caffeinated black hole?
Well, not quite, but you're catching on. And the amazing thing is, just like Dennis's mom could account for every block, physicists can track the quantity of energy through these different forms. That's the law of conservation of energy in action.
So we've got this fundamental law, this cosmic rule book, but here's the kicker. Feynman himself said we don't actually know what energy is at its core.
It's true. We can measure it. We can see its effects everywhere,
Right.
from the smallest atom to the largest galaxy. But its true nature is still a mystery.
That's both frustrating and mind-blowing at the same time.
Yeah.
We've got this powerful principle, and yet we're still figuring it out.
That's the thing about science, and especially about physics. Every answer leads to more questions.
Yeah.
But by following those questions, we unlock deeper truths about how the universe works.
Okay, we've established that energy is constantly changing, constantly on the move.
Right.
But how do we actually measure this elusive thing?
Yeah.
Especially something like gravitational potential energy.
That's where Feynman's knack for elegant explanations really shines.
Okay.
He guides us through this incredible thought experiment,
Hmm.
using logic and a bit of imagination to understand how energy from gravity works.
Okay.
And the best part is, we
Yeah.
don't need any complex equations or historical detours.
I'm all about elegant solutions. Let's hear it.
Okay, so imagine you're designing weightlifting machines.
Okay.
You know, those contraptions with pulleys and levers
Right.
designed to make heavy objects feel lighter.
I've attempted those at the gym.
Yeah.
Let's just say those machines and I have a complicated relationship.
Well, Feynman asks us to picture two types of these machines. Ones that are irreversible, meaning some energy is lost due to friction,
right.
basically like every machine in the real world.
Yeah.
And then there are idealized, perfectly reversible machines.
Okay.
These exist only in our minds,
Yeah.
but they're the key to unlocking this puzzle.
Okay, so these perfect imaginary machines are the secret weapon.
Exactly. Feynman starts with a fundamental truth. Perpetual motion is impossible.
Okay.
You can't get something for nothing. The universe just doesn't work that way.
Right.
Now imagine we could build a machine that lifts a weight higher than a reversible machine.
Okay.
We could then lower that weight with the reversible machine,
Uh-huh.
gaining back more energy than we put in,
Yeah.
creating perpetual motion,
Right. Right.
which we already agreed is a no-go.
I see where you're going with this. By acknowledging that limit,
Yeah.
we can figure out the maximum energy that can be stored and released.
Precisely. That limit, the one set by the reversible machine, is the key to understanding gravitational potential energy.
Mhm.
It's the energy an object possesses because of its position within a gravitational field.
Okay, that makes sense. But how do we actually apply this in the real world? Got any tangible examples?
Take a simple inclined plane.
Okay.
Picture a ramp with a gentle slope.
Okay.
You attach a 1-pound weight to a string at the top, letting it hang down.
Okay.
On the other side of the string, which is stretched over the top of the ramp, you have a weight we'll call W
Okay.
resting on the sloping surface.
Got it. Classic physics setup. So how do we figure out how much weight W needs to be to balance that 1-pound weight hanging down?
Since we're using our handy reversible system,
Okay.
we can think about the energy transfer as weight W sliding down the incline
Okay.
and lifting the 1-pound weight up.
Okay, I'm visualizing it. What's the key insight here?
The work done, the energy expended to move something, by weight W moving down the ramp has to equal the work done to lift the 1-pound weight up.
Okay.
And because energy is conserved,
Yeah.
it can't be created or destroyed, only transformed.
So we're essentially talking about a direct relationship between the distance each weight moves
Yeah.
and the energy needed to move it.
You got it. Now, to make things even more interesting, Feynman uses a specific type of inclined plane,
Okay.
one that forms a right triangle with sides in a 3-4-5 ratio.
Yeah.
The length of the sloping surface is 5.
Right.
The height where the 1-pound weight is hanging is 3, and the base of the triangle is 4.
Okay, I'm picturing it. So if the 1-pound weight is lifted 3 units.
Then weight W needs to move 5 units down the slope to lift it.
Okay.
And because the energy transfer has to be equal,
Yeah.
we know that W needs to be 3/5 of a pound to achieve perfect balance.
Wow, that's surprisingly straightforward.
Yeah.
I thought we'd be knee-deep in equations by now.
That's the elegance of Feynman's approach. And if you really want to be amazed,
Oh.
there's this brilliant visual proof
Okay.
devised by a 16th century scientist named Simon Stevinus.
Okay, I'm intrigued. What did Stevinus do?
He imagined a chain draped over a triangle
Okay.
with more links on the steeper side.
Okay.
The chain doesn't move
Okay.
because the weight on each side is perfectly balanced.
Okay.
And guess what? The ratio of the lengths of chain on each side
Yeah.
perfectly matches the ratio of weights needed for balance.
Oh, wow.
Just like in our inclined plane example.
That's incredible. A visual proof that brings the whole concept to life.
Yeah,
So this principle applies to any system where we're working against gravity, right?
you got it.
Okay.
From simple levers to complex machines, this understanding of potential energy helps us calculate the forces at play.
This is blowing my mind.
Right.
It's that we're unlocking the secrets of the universe with just a few core principles.
That's the beauty of physics, and once you start seeing the world through this lens of energy,
Yeah.
it's hard to go back. But remember,
Yeah.
we've only explored half the equation. We've
Right.
talked about potential energy, the energy of position. But what happens when things start moving? That's where kinetic energy enters the picture.
Okay, I'm ready for kinetic energy.
All right.
We've talked about the energy of position.
Yeah.
But things are rarely just sitting still, are they?
Exactly. Think about a roller coaster perched at the top of the highest hill.
Oh, man.
Right.
Talk about potential energy.
All that stored energy just waiting to be unleashed.
Right.
As the coaster plunges down that first hill,
Yeah.
the potential energy transforms into kinetic energy, the energy of motion.
So at the bottom of the hill, when the coaster is like screaming along at its fastest,
Yeah,
that's maximum kinetic energy.
exactly.
Okay.
And here's where it gets even more interesting.
Okay.
The kinetic energy of an object
Yeah.
depends only on its mass
Okay.
and how fast it's moving its velocity, not on how it got up to speed.
So a roller coaster car
Hmm.
and a car on the highway could have the same kinetic energy,
Right.
even though they took very different paths to get going.
Precisely. It's a universal form of energy.
Okay.
And just like with potential energy,
Yeah.
we have a formula to calculate it.
Okay.
Kinetic energy equals 1/2 times the mass of the object
Right.
times the square of its velocity.
Okay. I'm sensing a pattern here.
Yeah.
We've got these two main types of energy
Right.
potential. The energy of position
Mm-hmm.
and kinetic.
Mm-hmm.
The energy of motion.
Yeah.
Constantly like playing off each other, transforming back and forth.
And throughout all those transformations,
Yeah.
the total energy of the system remains constant.
Right.
It's a beautiful dance.
Yeah.
Energy flowing from one form to another,
Right.
never creating,
Yeah.
never truly destroyed.
Mind-blowing.
Yeah.
It's like Feynman said, Energy is the ultimate shapeshifter.
And remember all those other forms of energy we mentioned.
Yeah.
Light, heat, sound, even the bonds holding atoms together.
Okay.
They're all ultimately different expressions of this fundamental concept,
Okay.
often boiling down to kinetic energy at the atomic or subatomic level.
So when I warm my hands by a fire,
Yeah.
I'm basically feeling the kinetic energy of countless tiny particles.
You got it. It's all connected.
This is making me look at everything in a whole new light, literally.
Right.
So what was Feynman's takeaway from all this?
Well,
Why did he think it was so important for us to understand energy?
Feynman believed that understanding energy is crucial for everyone,
Okay.
not just physicists.
Right.
It helps us make sense of the world around us.
Yeah.
From the smallest interactions to the largest cosmic events.
Right.
He saw the law of conservation of energy as a powerful tool
A tool for what?
for understanding the limitations of the universe,
Okay.
for making predictions about what's possible,
Right.
and for driving innovation.
So like knowing we can't create energy out of thin air
Exactly.
pushes us to find new and better ways to use the energy we do have.
Exactly.
Right.
And to tap into those vast, untapped sources of energy all around us, like the sun, the wind, even the heat deep within the earth.
Like Feynman said, there's energy locked up in plain water. Imagine if we could unlock that.
That's the challenge he left us with.
Yeah.
To find safe, sustainable ways to harness those sources
Right.
and solve some of humanity's biggest problems.
Yeah, it's both daunting and inspiring. This deep dive has been a wild ride. Thank you so much for joining us, and until next time, Deep Divers.